Today's lesson is over section 3.4 again, day 2 of the chain rule. Here I have a warm-up problem, so if you could pause the video and give it a shot, that'd be great. Now here, once you're back, I need to use the product rule to help me simplify this. So I take the derivative of the first, which will be 2 sine of x, so breaking down the 2, but then the derivative of the inside, because it's really sine of x squared, would be cosine, then times the second, then plus the derivative of the second, which will be a 4 coming down, and then the exponent being 3, and then the derivative of the inside, then times the first. Here I want to be able to factor some things out, so it looks like I can take out a 2 sine of x and a x to the 5th plus x cubed all to the 3rd. And then that leaves me with cosine of x times x to the 5th plus x to the 3rd plus 2 times that 5x to the 4th plus 3x squared times sine of x. Now it looks like I can also take out an x to the 3rd out of the first two terms inside the brackets, and then an x squared out of the second two, which means I can only factor out another x squared and put it out front for the overall function. So unfortunately this one's not going to look super pretty once I'm done, but I can do a little bit of factoring to help clean it up a little bit. And so then this would be my final answer. Okay. Now the chain rule is said to, if you have two functions, it's kind of like a composition of two functions. And so when we take the derivative, it needs to be differentiable at x for the inside one and differentiable at g of x, whatever that x value is for the outside function. So I take the derivative of the outside with respect to the inside times the derivative of the inside. And so Leibniz notation allows us to make really difficult ones, kind of expand them out so it's a little easier, because sometimes the notation can be a little tricky. So here I'm going to show you what that looks like for letter A. I don't necessarily have to do this, but sometimes it is helpful. So I changed f of x to y to help me out a little bit. So here I'm going to say y is equal to cosine of u, and then that's dy over du is just negative sine of u, and then u portion is the 2x squared minus 3x. That gives me 4x minus 3. So then now once I have those two derivatives, I actually multiply them back together to create my derivative overall. But then notice that there's still a u inside of the sign. So that means I have to take what I set equal to u and plug it back in to get my original function, or my actual derivative. And so then that would be, so negative 1 times 4x minus 3 times sine of 2x squared minus 3x would be my final answer. Now you don't necessarily have to do this for everything. So like letter B, I can just rewrite this as tangent of x to the 4th power, and then use the power rule to do the outside, and then take the derivative of the inside and say it's secant squared. So it's not necessary to use Leibniz notation, but sometimes it can be helpful if you are not able to break them apart so easily. So letter C, I have e to the sine of x. So I take the derivative of the outside, which is just e to whatever is up in the exponent, times the derivative of the inside. In this case would be the exponent. So I would get cosine of x times e sine of the x. Here for D, I would take the derivative of the outside, which would be cosine, and then the derivative of the inside of that e to the x would just be e to the x. So that would be my final answer. So now sometimes you'll have a power where the base is a number to an exponent, and trying to figure out what the derivative there is. And so here's the proof. So using some exponential properties and rewriting some things, I can show that the derivative of any number to an x power will always be a to the x times ln of a. And so for example 3, I have one like that, which is 3 to the x. So that means it's 3 to the x times ln of 3. And that's it. That's all I need to do. Now letter B, here is a great place where Leibniz notation would help out extremely well. So I'm going to say y is equal to cosine of u, take the derivative of that, Then u is the next function inside, so tangent, and I can use whatever letter I want, so I'm going to use r, and so that gets me secant squared of r. And then r is the last one, which is sine of t, and then I take the derivative of that. And so then now, once I have all three of those, to get dy over dt, which is essentially what is the derivative overall that I'm looking for, I can take all those derivatives that I had and multiply them to each other. And notice that also cross-canceling, you're able to cancel out the du's and the dr's that allow you to get back to dy over dt. So then multiplying them all out, now notice I have a u and an r in there, so I need to plug in u and plug in r back into this function. So that gives me negative sine of tangent of sine of t times secant squared of sine of t times cosine of t. And that would be my final answer. Okay, thanks for watching.